When managing interleaved data, programmers face a specific constraint: executing a selective cyclic shift on a dataset without disrupting adjacent passive information. In Python, this translates to a specific requirement. We need to perform a right rotation of k steps exclusively on the even-indexed elements of an array, leaving the odd-indexed elements in their original positions. This diagram shows our starting state, a horizontal array of 6 nodes containing the integers 1 through 6. Below them are their zero-based index addresses, running from 0 to 5. To filter this sequence by index parity, we isolate the even addresses. Indices 0, 2, and 4 are the active targets, while the odd addresses at 1, 3, and 5 are designated as passive. If we apply a rotation factor of k equals 1, every active element must shift exactly 1 position to the right relative to the other even-indexed positions. The element at the final even index, index 4, to not shift further right, so it re-enters the sequence at the first available even position, index 0. Throughout this shift, the passive elements at the odd indices have not moved from their original positions. Manipulating interleaved data requires treating the list as 2 separate streams. Without this separation, a standard rotation would shift the entire block, causing the active data to collide with the indices reserved for the passive data. It is common for beginners to try solving this by reaching for Python's built-in array rotation tools. Applying a global function like collections.dq.rotate, a method for double-ended queues, fails here because it shifts the entire data block. It cannot distinguish between even and odd indices. Another approach is writing a manual loop that removes the last element with pop and moves it to the front with insert 0. This triggers a performance penalty. Because insert 0 forces the interpreter to shift every subsequent element in memory to create space, the operation results in a time complexity of O of n times k, which slows down significantly as the list grows. Solving this requires a 3-step method: isolate the target elements, rotate them as a sublist, and merge them back into the original structure. This approach relies on leveraging the way Python manages memory slices to perform operations more efficiently than a standard loop allows. The first phase is extraction. We isolate the even-indexed elements using Python's extended slicing syntax, nums.to. The step parameter, that final 2 in the slice, instructs the interpreter to grab every second element, starting from index 0, skipping the odd indices. The active elements detach from the main array to form a new compressed sublist, leaving the original odd-indexed elements behind. This slice operation creates a specific type of allocation in Python's memory. This is a shallow copy. As shown in this memory map, Python creates a new list structure, but the elements inside it are references to the exact same objects in the heap as the original list. This new list object protects the passive data. Because we are now operating on a separate container, any changes we make to the order of this sublist will not affect the gray elements still in the original array. Extracting a shallow copy is a reliable way to stage active data for transformation, ensuring the original sequence remains unchanged until we merge. In Phase 2, we prepare the sublist for the rotation. We have to handle a boundary issue. What if the rotation factor k is larger than the number of elements we're rotating? Rotating a 3-element list by 10 positions could lead to incorrect slice ranges.
We use modulo arithmetic to normalize the rotation factor. The modulo operator, the %sign, calculates the remainder of a division. By calculating k modulo n, where n is the length of our sublist, we ensure the rotation factor is always within the valid index range of the list. The modulo operator creates a circular index system, where elements can shift forward indefinitely without exceeding the list's boundaries. It functions like a clock. Advance 13 hours on a 12-hour face, and you land at 1 o'clock. 13 modulo 12 equals 1. This math ensures the rotation stays within the valid range of the list, preventing errors regardless of how large the rotation factor is. Phase 3 executes the rotation using slicing and concatenation. The formula uses 2 slices. First, even minus k, shown here in green, starts k steps from the end of the array. By using negative indexing, we isolate the elements at the end that are destined to wrap around to the front. The second slice is even. This captures the rest of the array, the elements that shift rightward but do not move past the end boundary. We use the concatenation operator.
the plus sign to join these two memory blocks as the elements shift. During concatenation, the tail elements move to the front, creating a new, properly rotated sequence. Because this operation relies on Python's built-in slicing, it is handled efficiently by the language's C backend. Negative indexing handles the boundary logic completely automatically, so we don't have to manually track pointers or indices. In phase 4, we return the rotated data to the original array without disturbing the passive elements. We use extended slice assignment. nums:2 equals rotated even. This is a critical distinction in Python. While slice extraction creates a copy, slice assignment modifies the original list in place. The rotated elements slot back into the even-indexed positions they were originally pulled from, while the gray elements remain undisturbed. The assignment physically overwrites the values at those specific even indices within the original memory allocation. A common error during this step is a value error caused by a size mismatch. Python will reject the assignment if the number of elements on the right side doesn't exactly match the number of slots available in the target slice on the left. When the sizes align, slice assignment allows for targeted updates, modifying only the even-indexed elements while leaving the rest of the structure perfectly intact. This three-step method, extract, rotate, and reassign, creates a clear pipeline for handling selective data manipulation. We can measure the efficiency of this method using Big O notation, which describes how an algorithm's resource requirements grow as the input size increases. This table compares slicing against our earlier alternatives for time and space complexity. Slicing operates in O of n time and O of n space. It's far more efficient than the manual loop, which carries a time penalty of O of n times k from repeated memory shifts. And while the dq.rotate function is very fast at O of k, it is not an option here because it cannot target selective indices. This makes slicing the most effective method for manipulating interleaved sequences in Python. Solving these problems effectively requires moving past the memorization of syntax to understand how Python handles data in memory. Performance in high-level languages often depends on how well we navigate the underlying mathematical and memory constraints of our data structures.